In our last video, we learned that recursion can be used to perform looping, and that every good recursive method is going to have a test for whether we're in one case or another, and possibly there'll be multiple recursive cases, multiple base cases, but it turns out we have to have at least one case with a recursive call if it's truly a recursive method, and we have to have at least one case, if we want our method to be useful, we have to have one case that has no recursive call, so that the program will eventually stop, the recursion will stop, and that case without any recursive call is called the base case. And we then analyzed some robot-related methods to see what behavior would arise from a recursive method, and I would like to take a look at some non-robot examples. So here's one. I have a method called p, and p apparently takes in a value n, and if n is 0 it returns 1, and otherwise it returns twice p of n minus 1. So this is a recursive method because it's calling itself. It's a potentially useful recursive method because it has a base case where it doesn't call itself, and a recursive case where it does. And actually we like the fact that the recursive case is on a different situation, is somehow closer to the base case, right? If we assume that n is greater than or equal to 0, which we better assume, if n is greater than or equal to 0, then if I say, for example, p of 5, this is going to call p of 4, which will call p of 3, which will eventually get down to p of 0 when the recursion stops. If I try p of a negative number, well, p of negative 1 will call p of negative 2, which calls p of negative 3, and will never reach that base case, and the recursion will not stop. So the intention of this method is apparently to call it where n is not negative. Let's find out what it actually does. To do this, in our last video I advised making a chart, so we're going to do that. And in this chart, we've got n, and we've got p of n, the input and the output. And I want to know, how does p of n, what p of n do I get back for a given n? And you might be tempted when you look at this chart to say 10. Let's see what it does for 10. But 10 is a very hard number to work out because there's going to be a lot of looping. So if we want to understand this method, I recommend starting very simple. So maybe you feel like, well, 1 is pretty simple. And I agree, 1 is pretty simple. But 1 is still pretty tricky, right? Because we're going to say, yeah, it's simple and it's tricky. Well, it's simpler than 10, but it's trickier than something. So when n is 1, we go to the recursive case, that's 2 times p of, and we have this recursion, and recursion scares us. Therefore, if we're scared of recursion, and we should be at least a little bit, the easiest case is going to be, what if n is 0? If we want to understand this method, let's understand what happens when n is 0. So if n is 0, it says it's going to return 1. And I think you and I can agree that p of 0 is 1. No doubt about it. Look, p of 0 is 1. How about p of 2? How about p of 1? 1 is now the next simplest value of n. If 0 is the simplest, 1 is the next simplest. And 1 is the next simplest because I know p of 1 will involve calling p of 1. When n is 1, 1 minus 1 is 0, and I'll call p of 0. That's how I know that 1 is the next value to try. Alright, so let's try it. Is n 0? Well, no, it's 1. Okay, so I'm supposed to return twice 2 times p of n minus 1. Well, what is n? n is 1. 1 minus 1 is 0. I knew it would be. P of 0, I don't have to work out what p of 0 is because I wrote it down. P of 0 is 1. So 2 times 1, which is 2. Let's try another value. What's the next value to try? Well, 2, because I know p of 2 is going to involve computing p of 2 minus 1, which is 1, and I already know what p of 1 does. So let's try that. If n is 0, well, it's not 0, it's 2. So we come down here, find n minus 1, 2 minus 1 is 1. P of 1, I don't have to reason this out, I wrote it down in my chart. P of 1 is 2. 2 times 2 is 4. Whoop, 4. Sorry about that. And I guess we should try another one, but maybe you're catching on to the pattern now. P of 3, well, 3 is not 0, 3 minus 1 is 2, P of 2, I know from my chart, is 4, 2 times 4 is 8. at this point, maybe you figured out that p of 4 is going to be 2 times p of 3. 2 times p of 3, that's 2 times 8, which is 16. And it looks like, in general, for a given value of n, this is finding, have you caught on? 2 to the n. 2 raised to the nth power. This is finding 2 to the n. And actually, if I look at it, it should make sense, because if I know this is 2 to the n, then it makes sense to me, because 2 to the 0th is 1, and I know that 2 times 2 to the n minus 1, let's write that down, 2 times 2 to the n minus 1, and I know this is 2 to the n minus 1, because that's what p means, 2 to that power. 2 times 2 to the n minus 1, well, that's 2, that's 2 to the first times 2 to the n minus 1, and we know in that situation I can add the exponents. 1 plus n minus 1 is n, 2 to the nth. So the formula makes sense. It's mathematically consistent. We know that 2 to the 0th is 1, and that 2 to the n is, in general, twice 2 to the n minus 1. That's why it works. Here's another way we could reason about this same problem. We could write out, suppose I wanted to find p of 3. I could work out, well, let's see, p of 3, that's really 2 times p of 3 minus 1. And then we can just sort of write out the whole sequence. In fact, maybe I'll write it out like this. 2 times p, well, that's 2 times p of 2, which is, let me make some room, 2 times p, well, p of 2 is 2 times p of 1. I'm skipping some steps, but I think you see where this is going. 2 times p of 1. And p of 1 is 2 times p of 0. And p of 0 is 1. P of 0 is 1. So this is 2 times 2 times 2 times 1, which is 8, which is 2 to the third. So there's another way we can work out the answer. Let's look at another problem. New problem. F takes in a value n. If n is less than 3, it returns 1. This is the base case. There's no recursive call here. But otherwise, it returns f of n minus 1 plus f of n minus 2. So in our recursive case, we actually have 2 recursive calls. 2 recursive calls. Okay, I think we get the idea there. 2 recursive calls. So that's going to make this maybe even trickier to analyze. But if we go to our helpful little chart, n and f of n, we can actually work this out pretty easily. What would be a simple value of n to try? Well, anything less than 3 is 1. So how about 2? F of 2 is 1. That's what it tells me. Let's try something fancier. Let's try higher values of n. It looks from this code that higher values of n will be trickier. So a higher value of n would be 3. And to find f of 3, I find f of, what's 3 minus 1? It's 2. F of 2 plus f of 3 minus 2 is 1. So this is f of 2 plus f of 1. F of 2 plus f of 1. Well, I know what f of 2 is. It's 1. But I don't know what f of 1 is. Maybe I should have worked out f of 1 already. Let's do that. F of 1. Well, let's see, 1 is less than 3, so it must be 1. Okay, now we're ready to try 3. F of 3, that's going to be f of 2 plus f of 1. That's f of 2, which is 1, plus f of 1, which is 1. So this is 1 plus 1, or 2. Let's try one more. F of 4. Well, 4 is not less than 3, so that's going to be f of 4 minus 1 is 3, plus f of 4 minus 2 is 2. So f of 3 plus f of 2. F of 3, here's f of 3, plus f of 2. And if I add those values together, 1 plus 2 is 3. Maybe one more. F of 5. Let's see, 5 is not less than 3, so we find f of 4 plus f of 3. F of 4, no, I'm sorry, I have these arrows. F of 4, that's this one, plus f of 3, and if I add together those two values, 2 and 3, I get 5. And at this point, you may see where this is going. This is actually finding the nth Fibonacci number, right? The nth Fibonacci number is always the sum of the previous two Fibonacci numbers. That's why you see this f of n minus 1 plus f of n minus 2. So if I want to find 6, f of 6, I add up f of 4 plus f of 5, which is 8. F of 7 will be f of 5 plus f of 6, that's 5 plus 8, which is 13, and so on. But I want to show you a second way that we could reason out this program here, and that's using something called a recursion tree, or just a call tree. Recursion, call tree, something like that. And for that, if we want to find, say, f of 4, what we do is we say, well, 4 is not less than 3, so that's f of 4 minus 1, and f of 4 minus 2, that's f of 3 plus f of 2. So we'll write that out. F of 3, 3, and f of 2. Well, what's f of 3? It's going to be, I can reason out, f of 2 plus f of 1. And our chart is getting bigger. How about f of 2? Well, that's actually f of 2, that's an easy case, right? F of 2, that's less than 3. So when we get down to the base case, we know the answer. F of 2 is 1. F of 1, well, that's less than 3, so it's 1. F of 2, that's less than 3, so it's going to be 1. And because we see this plus sign here, that tells us we're going to add the numbers up. So that's 1 plus 1, so this one must be 2. 2 plus 1, this f of 4 must be 3, so f of 4 is 3. If we wanted to find f of 5, we're going to have a much bigger call tree, but we can get the answer pretty straightforward from that too. So here are a few methods that you can use when you're given recursive code to figure out what exactly is it doing. I'll see you in the next video, where we'll probably start learning how it is you can write recursive methods, how you can solve a problem by using recursion deliberately. I'll see you there.